Here comes a VLF reception challenge, comparing a resonant 1 meter loop to a much bigger one. In addition, we are trying to pinpoint the direction of incoming signals. Among other interesting signals, you can receive this on VLF. It's coming from an impressive and unique World Heritage Site. Although the system is more than 100 years old, SAQ Grimeton is still transmitting on special occasions. Receiving the signal from the electromechanical alternator transmitter is always a highlight for listeners. By the way, you're getting a nice EQSL card for your reception report. For the event on Christmas Eve, I built a compact rotatable indoor loop. It's promising, since I tuned its resonance to 17.2 kHz. Capacitors for frequency tuning are simply connected to the terminals with the knurled nuts. And yes, this is actually a foot-turning plate I swiped from the kitchen. Kudos to my wife, she always has the best ideas. It's perfect for mounting the antenna together with an angle scale. On our playlist Antennas and Wave Propagation, we are showing how to build VLF loops yourself with simple means. Today we are comparing the compact loop's performance with a bigger one, and we are determining a signal's incident angle. Since I predicted the latter one with our self-made Excel tool, I'm particularly excited about the result. If you are interested to try it, I would be happy to send you a beta version. By the way, you should definitely try this. If you are interested in electronics, you have come to the right place. PCBWay has great offers for both professionals and hobbyists. The sponsor of this video not only offers fantastic products, but also excellent service at fair prices. And look at this! The PCB Project Design Contest is going to be really exciting this time. Take the easy way with, you name it, PCBWay. With 10 to 100 km wavelengths, VLF signals are propagating straight and are barely affected by obstacles and weather. Due to their vertical polarization, you're achieving best reception using an upright loop. And this results in a horizontal radiation pattern with 2 main lobes and 2 zeros, allowing you to cover 360 degrees by just 180 degrees rotation. Using this angle scale, I don't have to rack my brains about north direction and the correct definition of the azimuth angle. Simple but effective. When I want to align the antenna with a signal, I can directly read the angle of both beam directions. Just align 0 degrees to exactly north, and off you go. As a test signal, I'm using Ronay in France, call sign HWU. Like most VLF stations of this type, it has an impressive antenna array with a diameter of about 2 kilometers. The light green color is roughly indicating the area where the grounding network is buried. Tall antenna masts at the corners and in the middle are carrying the wires for the so-called top hat capacitance. According to my tool, it's 633 kilometers from here, and the angle of incidence of the 18.3 kHz signal should be 252 degrees. For the best signal, you simply need to align a main lobe to the incident angle. I'm visualizing this on an azimuth map so that it doesn't get too confusing what I'm telling you here. I'm actually getting the best signal at approximately 250 degrees. Great, but it's even getting better. The other way round, you can determine the signal's angle of incidence to pinpoint the transmitter's location. The maximum signal is giving you a rough direction only, as the main lobe's beamwidth is wide. However, the antenna diagram's nulls are sharp and therefore well suited for this purpose. They are shifted 90 degrees relative to the main lobes. So I should find one at 252 plus 90 equals 342 degrees. And indeed, the signal is dropping by 30 dB almost exactly at 342 degrees. The signal must be coming exactly from the predicted direction. I'm estimating plus minus 2 degrees accuracy for my setup. Cool! My suspicion was rather that electromagnetic fields would be distorted by the walls of the house, making direction finding impossible. Of course, direction finding would be more accurate in an open field, but apparently it works quite well inside my office. The angular accuracy is more than sufficient to find the direction for the best signal. With the wide main beams, there's even 20 to 30 degrees room to null out interference. This makes wave hunting even more fun. Now, how does the compact loop sensitivity compare to larger, non-resonant ones? It's tuned for receiving SAQ Grimeton, but its frequency bandwidth is sufficient to receive the 18.3 kHz signal from Ronay. With a diameter of only 1 meter, it's delivering over 10 dB more signal in comparison to a 2 meter non-resonant loop we built earlier. That's remarkable, and I'd like to put the result into context. You know this diagram from previous videos, showing the antenna signal for a given field strength in the frequency range of 0 to 500 kHz. And doubling a loop's diameter is increasing its signal strength by approximately 9 to 10 dB. And the signal measured with the resonant 1 meter loop is more than 10 dB stronger than the signal of the orange 2 meter one. So it's playing in the 4 meter class. We achieved this by making it resonant and optimizing its Q factor. We will have a dedicated video on Electronics Unmasked demonstrating the full potential of this method. Even though I had no doubts about my antenna's performance, it's always very exciting to receive SAQ Grimeton. The compact loop received the signal with significantly better signal strength and SNR. An improvement of more than 10 dB over the non-resonant 2 meter loop is confirmed here as well. Once tuned with the right capacitance, the compact loop is delivering a great signal. Direction finding works perfectly, and it's fascinating that VLF signals are behaving exactly as predicted. Optimization of Q is very interesting. Don't miss the coming videos about building and optimizing resonant loops. Now stay tuned and don't forget to support the channel. See you soon in the coming episodes.